All right, let's dive into a real chemical showdown. We're talking about a high-stakes battle between different elements, where the grand prize is the electron. And believe me, the winner gets to power our entire world. You ever stop and think about what's actually going on inside a battery? It's not some kind of magic. It's basically a chemical fight club. You've got some substances that are like electron bullies. They're just determined to steal them. And then you have others that are, well, more willing to give them up. That transfer, that movement of electrons is what creates an electrical current. Harnessing that flow is the secret sauce to everything. So, to figure out who's going to win these fights, you got to know the players, right? Just like in any sport, we have a way to rank their strength, a way to see who's the heavyweight champion and who's, the underdog. And that ranking system, it's called the standard reduction potential, or E0. The easiest way to think about it is like a power level. It's a number in volts that tells us exactly how badly a chemical wants to snatch electrons. The little naught symbol just means we're measuring it under standard lab conditions. Now, this tendency to gain electrons is called reduction, and the opposite, losing them, is called oxidation. So a higher E0 value means a stronger pull, which makes it a really powerful oxidizing agent. Okay, so here it is, the official league table for today's big showdown. Just look at chlorine at the top, with a massive positive 1.36 volts. That is a serious contender. And then way down at the bottom, you've got potassium with a big negative value. That means it's way more likely to lose electrons than to gain them. This table right here is going to be our playbook for predicting the matches. All right, we've got the rankings. Time for the warm-up rounds. We're going to look at 3 different test tubes, each with its own unique chemical mix, to see where a reaction will actually, spark to life. First up, test tube 1. We've got a mix of potassium chloride and zinc chloride. So what's actually floating around in there? Basically, potassium ions, that's K+, and zinc ions, Zn2+. So is anything going to happen? Are we going to see a reaction? Let's check those power rankings again. Zinc is at negative 0.76 volts, and potassium is way down there at negative 2.93 volts. Both of them have a negative desire to gain electrons. But more importantly, and nope, nothing. It's a total dud. But why? Well, think about it. Both of these ions have already lost their electrons. They're both on the hunt to gain electrons to get back to being neutral metals. You can't have a fight if both guys only want to win and there's nobody there to lose. It's like having 2 goalies and no strikers. Nobody's giving up the ball. Okay, on to test tube 2. This time, we're mixing potassium bromide and platinum bromide. Now, this is interesting. We've got bromide ions, which have an extra electron to give, and platinum ions, which are short a couple and really want some. Now we've got a real potential matchup on our hands. This is looking way more promising, right? So will they go for it? Let's check the board. Platinum. Man, it's got a strong pull at a positive 1.20 volts. But look at bromide. It's also pretty high up there at plus 1.09. That means its ion, bromide, is pretty comfortable holding on to that extra electron. And the verdict is still nothing, no reaction. So what gives? Even though platinum is technically stronger, bromide is just too stable. It's holding on to its electrons so tightly that the small difference in their power levels just isn't enough to force a transfer. It's a classic standoff. Okay, now for the main event, our final test tube. We're mixing platinum chloride with zinc iodide. And the 2 key players in this ring are the powerhouse platinum ion and the iodide ion. And this is where it gets really exciting. We've got our champ, platinum, at a whopping positive 1.20 volts. Its opponent this time, iodide. Now, if we look at the ranking for iodine, its potential is only positive 0.54. That is a huge difference in power. The stage is officially set for a real chemical battle. And boom, we've got a reaction. The platinum ion is so much stronger, it just rips the electrons right off of the iodide ions. This is your classic redox reaction in action. The iodide gets oxidized, it loses electrons, and forms iodine gas. The platinum gets reduced, it gains them, and becomes solid metal. A clear knockout. Okay, so it's cool that we can predict a reaction, but what if we want to actually use it, like turn it into a battery? To do that, we need to figure out the exact amount of electrical push, the voltage, it can generate. Let's go back to that standoff we saw between platinum and bromine. We said nothing happened under standard conditions, but what if we cheat a little? What if we change the concentrations? That's where this beast, the Nernst equation, comes in. It lets us calculate the voltage when things aren't standard. So first, we find that standard potential. Yeah, it's negative 0.11 volts, which confirms it shouldn't work. But then we calculate this thing called Q, the reaction quotient. It's basically just a ratio of how much stuff we have. In this case, it comes out to 1.11. Now we plug all of that into the equation.
And we get positive 0.14 volts. Now that is the key takeaway here. Even though it looked like a dud on paper, just by tweaking the concentrations, we made the reaction happen spontaneously. This is literally how chemists and engineers fine-tune the power of real-world batteries.
But just when you think you've got the rules figured out, chemistry loves to throw a curveball. What happens if we bring in a totally new challenger, a real monster contender? So we're going to take our platinum setup, but we're swapping out bromine for fluorine. Now, if you know anything about chemistry, you know fluorine is the undisputed heavyweight champion of grabbing electrons, the most electronegative element there is. So what happens when you put the king in the ring with a strong contender like platinum? You get a voltage of negative 1.67 volts. Whoa, hold on. That's not just negative. That is a huge negative number. What in the world is going on? Did we build a battery backwards? Well, yeah, essentially. A big negative voltage like this just means the reaction is absolutely not going to happen the way we drew it up. In fact, the electrons want to flow in the complete opposite direction, and they want to do it with some serious force. Fluorine's pull is just so overwhelmingly powerful that it completely flips the script. But this surprising result, it's actually super useful. It gives us a whole new piece of the puzzle. We can now rank our players not by who's best at taking electrons, but by who's best at giving them up, the best reducing agents. You see, that huge negative voltage tells us something really important. Because fluorine is such an insane oxidizer, it wants electrons more than anything, that means its other form, the fluoride ion, has to be the exact opposite. When you force the reaction backwards, that fluoride ion becomes the strongest reducing agent we've seen. It can be forced to give up its electron more easily than any other. And that lets us build out this final complete ranking, from fluoride at the top all the way down to chloride, which holds onto its electron for dear life. And that really brings it all together. We've seen how these power rankings let us predict what's going to happen, and even how to harness that energy. So it leaves me with one final question for you. Now that you know the rules of the game, if you could pick any two elements from the entire periodic table, what would you choose to build the ultimate battery? Something to think about. Thanks for tuning in.